Let us continue our discussion on rotational motion. Here in this video I am going to introduce you to two terms, moment of force and angular momentum. Let me begin with the moment of force. So once again we will take example of a body performing rotational motion. But before that, let us say we have an irregular shaped body, and let us again say it has some mass, and let us say this has got mass m, and let us say I am applying a force F on this body. And what will happen is that when we apply a force on this particular body, there will be a change in velocity. Of course, this is assuming the force is sufficient to cause motion of the body, or if it is already moving, to change the velocity. So basically, when we apply a force onto a body, right, which is performing or which is allowed to perform motion in plane or plane motion or translational motion, right? So translational motion, right? So when this body is free to move in a plane, right, either in this direction or maybe at an angle along two axes, right, or maybe even along three axes, right, what happens is that the change in velocity of this body, for a given mass depends only on the force applied. Let me repeat. Here I am talking of a body which is performing motion in a plane, right? We're not talking of rotational motion as yet, right? I'm just taking an example of a body which is free to move in this particular direction, right? Along the x-axis and along the y-axis, and its mass is m. Supposing we keep the mass constant. If the mass is constant, the change in velocity, increase, decrease, or whatever, depends only on the force applied. That is in case when the body is performing motion in two planes, or is performing motion in one plane or in one dimension. But if I take the same body, right, let me again draw the same body. I hope it's looking same, even though they might look a little different. Assume that they are same. So if I apply a force F on this body, but this body is able to rotate or turn around an axis of rotation. It is the axis of rotation. In this case, what will happen is this body will start performing rotational motion. So it will start moving in a circular path, right? It will start performing rotational motion. That will also cause a change in velocity. Right? But there's a difference. This change is in the angular velocity. Right? Because here we are talking of a body performing rotational motion. The change is in the angular velocity. Also, the change in this angular velocity depends not only on the force F, right? We'll call this force F. The same force is over here. It does not depend only on the force F. It also depends on one more factor, and that factor is the perpendicular or the shortest distance between the axis of rotation and the line of action of force. So this change in angular velocity does not depend only on this force, but it depends upon the perpendicular distance between the axis of rotation and the line of action of force. Let me show it over here. This is the force, right? This is the line of action of the force if I extend it on either side. And this is the axis of rotation, the perpendicular, the shortest distance. So from this point, I drop a perpendicular on the line of action of force, something like this distance. So the change in this velocity, let us say this force is increasing the velocity. So the increase in velocity not only depends upon this force, but how far it is from the axis of rotation. If I apply force further away from the axis of rotation, the angular velocity will increase more. If I apply force very close to the axis of rotation, the change in velocity will be lesser. Right? And all of us have experienced that in day-to-day life. For example, if I take this common example that we always take up when we are discussing moment of forces, let us say there's a door with these two hinges. So if I want to swing this door in this particular direction, generally we apply force over here because we want to move away maximum distance from the axis of rotation. This is the axis of rotation, and this particular force, the line of action of force, which is going into the plane of this page, this is the distance. And if we want to keep this distance maximum, so that we have to apply less force. If I apply force over here, we know that we'll have to apply a larger force to open or close this door. So whenever we are talking of rotational motion around an axis of rotation, the change in velocity depends on two factors. One is r, which is this distance r, distance between these two, and the force also. Whereas in this case, it depends only on force. And this particular term, r into force, right, which leads to rotational motion, is known as moment of force, or the more popular or common word torque, which is denoted by the sign tau. This is read as tau. Right? So this was the point which I wanted to stress upon over here, that whenever you see a body performing rotational motion, there is a force being applied which is at some distance from the axis of rotation, and in that case we say that the force is exerting a torque on the body. Right? So whenever you see a body performing rotational motion, you will immediately understand that torque is being applied. That means the force is causing the body to rotate around an axis, and that is given by r into F. Right? So this torque is r into F. The unit would be Newton meter, and as you would have guessed that if r is 0, right, that means r is 0, that means the force is being applied on the axis of rotation. So if this is the hinge of the door, and if I apply force on the hinge of the door, perpendicular over here, I will not be able to open or close the door. The door will not swing, the door will not open or close, because there is no torque being applied, because this term will become equal to 0. Right? So this is moment of force or torque, and it is given by r into F, unit is Newton meter. One more term which I want to introduce over here is angular momentum. Angular momentum. And it is also known as moment of linear momentum. Right? Same example I can take. Instead of force, if I consider, let us say there's a momentum P acting in this direction, right? I don't want to draw the diagram again. Instead of F, you say P. Then what I will get is that it will lead to angular momentum. In this case, it would be simply linear momentum because of this force. In this case, this particular momentum will lead to angular momentum because we are talking of a body performing rotational motion. And angular momentum is denoted by the symbol J, and J would be given by R into P, where P is linear momentum. And J is the angular momentum. Same concept, because the angular momentum would depend not only on the magnitude of this linear momentum but also the distance from the axis of rotation. So J is R into P. So the word moment, automatically whenever you come across the word moment, it means, or it is connected to the distance from axis of rotation. So whenever there is, for example, moment of force, automatically means that we are talking of force and the distance from the axis of rotation. Similarly, moment of linear momentum would mean P into R. Right? So in physics, whenever you come across the word moment, immediately understand that there's something to do with the distance from the axis of rotation. Right? So I just wanted to introduce to you these two terms, moment of force and angular momentum. And once again, to summarize this video, to sum up this video, what I want to stress upon is the fact that whenever we are looking at rotational motion, it is the torque, the momentum which causes the rotational motion, not the force. Right? Force plus distance from axis of rotation. This combination is responsible for rotational motion, and this combination is known as torque or moment of force. Right? Okay. In the next video, we will look at a few more terms associated with rotational motion and the interrelationship between these terms. Thank you.